you. Today I will just do 1 hour and or a little bit less, and I will talk about a really important algorithm, probably the most important one in today's distributed systems. First, a few seconds of pause for the Ukrainians who are fighting for their freedom and for our freedom. So, consensus. Consensus is probably the most important algorithm in large distributed systems, and today's internet survives because of consensus. And actually, it's very interesting. Today, it is probably the most important algorithm. But maybe in 20 years, it will not be. It will be something else. And if I have time in the course, I will explain how I think it's going to go. It's kind of like today, internal combustion engines are very important. The whole industry is riding on them. But in 20 years, it will all be electric, okay? And it will be more efficient. But today, it is true that all the heavy lifting is done by consensus. In consensus, conceptually very easy. All the nodes are proposing some value, and they run some algorithm, and then they have to agree. And many problems are based on consensus. We already, actually, in the very first lecture, remember I talked about total order broadcast, also known as atomic broadcast, which is equivalent to consensus. Also, databases that do transactions, distributed databases, have to agree. And other kinds of algorithms, like terminating reliable broadcast. If the nodes do reliable broadcast, they don't actually know when it's done. You can see it from the outside, the God's eye view, time-space diagram. But the nodes themselves don't. And if you want them to know it, they have to do consensus. Okay. So many tools on the internet are using consensus, and if you're following other courses like cloud computing, you will be using them. Transactional database, log management, orchestration, cloud tools, thing called Zookeeper from Google and so on. It's all using consensus. Inside. Even if you don't know, it's using consensus. And I like to say consensus can do heavy lifting. It's a very strong algorithm, consensus. It can do strong things, okay? Okay, so that's a very nice introduction for this algorithm. So what is it? Well, I'm going to define it exactly the way I defined the other ones, with the properties, and then it will have an interface. And the properties, you see, in some ways they're kind of similar to reliable broadcast. There's 4 properties. Validity, that means it's basically doing the work. Validity for reliable broadcast means when you send it here, it actually is delivered there, okay, under some condition. Here also, any value that you decide is a value that has been proposed by somebody. Agreement, again, it's intuitively kind of similar to the agreement of reliable broadcast. Here, no two correct nodes decide differently. So all nodes have to decide. That's the thing. You propose, and then they all decide. And they will not decide differently. And every correct node will eventually decide. That's termination. And also, you decide it most once. Once you decide, it's over. You can't just change. Okay? That's integrity. That means you have integrity. That means you're like honest guy. You won't change your opinion. Okay? You decide at most points. This is consensus. Okay? So here's an example. We have 3 nodes. This one proposes 0, proposes 1, proposes 0. This one decides 0, this one decides 1 and then crashes, and this one decides 0. Okay, so does this execution satisfy the properties I just showed you? I recall them very quickly. The important one here is maybe C2. So does this satisfy consensus? What do you think? I know your brains are maybe used up after the midterm, but try to restart them again. What do you think? Is that consensus?
Yes.
Yes? Why?
Because every correct node decides on a value and it's the same value.
Exactly. Every correct node, no two correct nodes are deciding differently, so they're all deciding the same. This one decides differently, but it crashes, so it doesn't count. Okay? Doesn't count. No two correct nodes decide differently. So that is definitely consensus. Now, you can already imagine that there's going to be another version of this algorithm. Remember, we had reliable broadcast and uniform. Uniform means that the failed nodes, what they do is important. Here we have a no two correct nodes decide differently. So you can imagine there's also a uniform version. So that means that the failed nodes' decisions are important. Okay? You see that done? So there is, in fact, a uniform version of this. This one is called uniform consensus. Here we're also worried about the failed nodes. That's important, huh? Because if a transactional database does a transaction and it fails, did that transaction get put on the database in the stable storage or not? Well, maybe it did, okay? And in order to make sure that there's no problem with the transaction deciding differently, it should be a uniform agreement, okay? So for things like distributed databases, this is the one that's really the important one, okay? Because when you have an action in the real world, it might be done before the failure, okay, or not. You don't really know. So it's important. So this is the important one, okay? And it's not easy to do this one. We will see. To do it really well for the internet is not going to be easy. Okay, what about this execution? Is it uniform consensus? It's the same one as I showed before. Huh? What do you think?
No.
No. Why not?
Because this time we take into account the also the failed nodes.
Also the failed nodes. So P2 here, who crashes here, and P2 actually decides before crashing, and decides 1, and these decide 0. So this is not uniform. Huh? Uniform is that all the decisions, even the failed ones, have to be the same. Okay? Okay? So that's the whole specification. So it's a very easy specification, huh? And there's 2 events. There's a request. Every node proposes, sends value down. So in some sense, all the nodes are working together, huh? If you do a transaction, every node has to initiate the transaction, proposing something, commit or abort. And then the algorithm runs, and eventually every node will get the decision coming back, indication coming back up, satisfying the 4 properties. Okay, so as usual, we will start with a P version, perfect failure detector, and it will be actually a very nice algorithm, but of course depending on P, so not yet full internet. Huh? This is an algorithm called hierarchical consensus. In general, the full uniform consensus for internet is actually a complex algorithm to do it right. That's why we start with a simpler one, which is this one, hierarchical consensus. This one is using perfect failure detector and best effort broadcast. So it's kind of similar requirements to reliable broadcast. Huh? So every node has a local variable called proposal, and every node, some node is going to be like the node that you adopt the proposal of. So everybody's going to take the proposal of node 1, for example, or node 2. And there's going to be another local variable, last proposer. This is the node that you actually take the proposal from. So every node is going to somehow pick another node and say, this is the proposal I'm going to decide on. And that's the last prop, okay? And the algorithm has a very interesting structure. It uses rounds, like boxing match rounds, okay? So all the nodes will be in round 1, and they will run, and they all know they're in round 1. And then they will all pass to round 2, and then they will all run in round 2, and it will go all the way to n. So this algorithm will always go from 1 to n, okay? It will always go through all rounds, okay? And it starts round 1. So all the nodes start in round 1, and in round I, so starting with 1, I is the leader. So node 1 starts out being the leader. It broadcasts its proposal, and it decides. That is the decision, okay? And if node 1 does not crash, that's fine, right? If node 1 does not crash, then all the other nodes will get V, they will adopt V, and they'll remember that node 1 is the guy telling me, okay? So if node 1 does not crash, that's it. That node's 1 proposal is it, okay? But maybe node 1 crashes. And in that case, we forget node 1. So we detect the crash of node 1. In some cases, it might crash. And then we go to round 2. And in round 2, node 2 is the boss. Node 2 broadcasts. And if node 2 is correct, then everybody will adopt the proposal 2. So you see, it's very systematic, huh? There will always be an earliest non-crashing node. Now, that's a property. If we assume that not all nodes crash, then there will be some node that doesn't crash, which is the earliest one. Maybe it's number 1 or 2 or 3. And that's the one that's going to give the winning value, the value that we decide on. Because in round 3, for example, round 3, node 3 will broadcast, and everybody will adopt that value before going to round 4, okay? So you can kind of imagine that one of the tricks is, how does the node know when it goes from round 3 to round 4? It's not synchronous, huh? We're not in a synchronous thing. So somehow the nodes have to know when they go to the next round. And that's one of the things of this algorithm. That's one of the things that makes it work. And we'll explain, how does the node know when it goes to the next round? Okay? Okay, so the basic idea, which I mentioned, there must be a first correct leader. So some of the nodes are going to crash anytime, but there will always be one that doesn't crash, and there must be, we take the earliest one, the one with the lowest number. And that one, let's say P, that one will broadcast some value, and because it's best effort and P is correct, everybody will get it. Okay? See that? every correct node adopt V. So we're only worried about correct nodes here. For the moment, we're doing regular consensus. So all the correct nodes will get the V and adopt it. And in the future rounds, they will all know V. So whatever happens, V will be the decided value. Okay? That is the idea. Now, to make this work, we have to be careful that every round is really separated from every other round, and then all the nodes kind of in a nice way go from one round to the next. And you can say, how can we do that? That's kind of like synchronous, and we're not synchronous, okay? But the trick is we can do it. We can actually do that. And I'll show you how it works. Okay, so here's an example. 3 nodes, 3 rounds. This one proposes A, B, and C. They each propose a different value. Okay, and now this runs. So the first one, it starts in round 1. So the first one is the boss, decides A. Okay, oh, great. But then it crashes. Okay. And then we go to round 2. So I'll explain how it works. But all the nodes that are correct will know. They will go to round 2. And P2 is the boss in round 2. And it doesn't know A. It knows B. So it decides B. Okay. Great. And the B is broadcast and it will arrive at node 3. See how it works? But there is one little problem that we have to worry about. P1 here, it's dead, okay? It died here, but the messages might still be in the network. There might be an old message from P1 that still manages to get to P3, and that contains A. And this is called an orphan message because it has no parent. Poor message. The parent node is dead, but the message is still around. Okay, this is perfectly possible. In real networks, this is absolutely possible. Okay? It happens. So we have to solve this problem. Okay? We have to somehow take care of these orphan messages. But if we can do that, then we're golden, then we're good. Then we have a working algorithm, huh? So if we don't solve the problem, then this message arrives, the proposal will be A, and this node will decide A, this one has decided B, and it's wrong, okay? So we have to do something about this. Can you imagine? How do we take care of these old messages? So they're basically messages that are leaking from previous rounds. Around when another node was the boss. Okay? So the trick is, how do we kind of insulate the rounds and prevent these orphan messages from leaking between the nodes? Well, you can look at, it's actually not so hard to insulate. If you look at this orphan message, it's coming from round 1, it's coming from P1. But we're already in round 2, where P2 is the boss. Okay? And 1 is less than 2. So somehow, we can tell it's an old message we notice it's coming from previous round. So somehow, we can actually ignore these messages because we can tell they're coming from earlier rounds. And that's the trick, okay? If we do that, then we're good, okay? So we only adopt a message if the number increases. So here we have a 2, and now we have, which is already the round 2, but now we have an old message from round 1, which is less than 2. So we can ignore it. But we might, maybe P2 crashes, and we'll have another message with last prop equal to 3. So if the number increases, we can take it. But if it doesn't increase, we can ignore it. Okay? See how that works? So that's the trick for insulating the rounds. Okay? So we can avoid these orphans. So here's the summary of the problem. The leader in round R might crash, but still there's a message that much later will affect a node in a round bigger than R. Some old message. The way to get rid of that is to order the nodes, to give them kind of rank. 1, 2, 3, P1. So we have higher ranks for the earlier ones. Okay? And we only adopt if it's later. So here, if it's ranked lower. Okay? If it's not lower, then we know that it's an old message. Because P has crashed, we know that it must have crashed and should be ignored. Okay? So there's like a Boolean condition there. Okay? So here's kind of how the thing works. So here we have 3 nodes, again, proposing ABC. 3 rounds. Okay? Now, in round 1, P1 decides A and does best effort broadcast. The A goes both there and there. Okay? Then, notice locally, these 2 nodes adopt that proposal. They replace the B by A, C by A. The last prop becomes 1. Okay? And then we go to round 2. And in round 2, P2 is the boss. So P2 will decide A. Well, it doesn't make any difference because it's the same value here, okay? And of course, P1 already decided. But since none of these nodes failed, we know this is not going to change anything, okay? If there is failure, it will change something, huh? If node 1, P1, fails here, then there might be a change. Depending on whether this message actually made it to P2 or not, P2 might decide B, okay? If there's a failure. But if there's no failure, it doesn't, okay? And in round 3, very nicely, P3 is the boss, and P3 also does broadcast. So the thing is, all the time you do all the rounds, okay? Whenever you run the algorithm, you cannot skip any rounds. You have to do always 1, 2, 3. And the reason is that if there's a failure, it still has to work. You don't, if there's no failure, if you know for sure there's going to be no failures, then you don't really need to do all that, okay? But you don't know that. So that's why you have to do all rounds, okay? So here's another example with a failure, okay? So say now P1 decides and then fails, but it sends messages, and some of the messages, they make it, and some they don't. So we don't know which, okay? So let's say this one makes it, but this one doesn't. Okay, now we go to round 2. And in round 2, P2 is the boss. And it never got the A, so it's going to decide B. Okay? Now the B message comes here. Now, this is not an orphan, because the last prop is higher. This is coming from a higher number, so we can accept it, okay? It's not an orphan, so this will override the A, okay? So it overrides, and then we go to round 3, and then 3 is the boss, P3 is the boss, and it knows B and it decides B. So we notice that both P2 and P3 have decided B, so we're good. Of course, P1 decided differently, but it crashed. Okay, so this is not uniform algorithm, huh? Okay? Yeah, so I already answered this question. Huh? Is this algorithm uniform? No, huh? Because this, when a node decides and then crashes, the next round will override that. Huh? So this is not uniform, but we will make it uniform after. Okay, so this is not uniform. Okay, so let me show you the code now. So it's 2 pages of code. It's not really very complicated, but there's a little bit of bookkeeping we have to do. We use best effort broadcast and perfect failure detector. We have some local variables. We have the detected, which is basically the set of nodes that crash. We have the round number, which is incrementing from 1 to n. Okay. We have the proposal. It starts out being undefined, so this symbol means undefined. And the last prop starts being 0. Okay. And then we have some bookkeeping messages for the rounds, which we will see, whether the messages are delivered or not. And we have our perfect failure detector, which gives us the crash messages, and these are added to the detected. So detected tells me which nodes that I know have crashed. Okay, so that's all bookkeeping stuff. Okay. So this is the actual code of the algorithm. So it's 1 page, and most of it is very simple. When I propose, it's very simple. The unbound, the undefined value becomes v. Okay. Okay. Now, let me step through this. Okay. This one will only change the value. Notice that if this local node already has a value, I won't change it. It only can be run if the value is undefined. Okay? That because we never know, of course. The propose, when I do the propose, maybe things have already advanced. And in that case, I can't change things anymore. Okay? So here is kind of the decision. Okay? So, the decision, there's some conditions here. Notice there's no message arriving. This is like a Boolean condition. Huh? So round equals rank self means I'm the boss. I'm in the round where I'm the boss. Okay? Broadcast is just like to avoid duplicates, I'm only going to broadcast once. Broadcast, false means I have not broadcasted yet. And then I set it true. And then I decide. And I do my best effort broadcast. So this is when the leader node decides. Okay? That's how it decides. And it decides permanently. It permanently decides. Why is it permanent? Well, it has to be because of the property of integrity. Once I decide, it's over. I'm only allowed to decide once. Yeah?
If we're using leaders anyway, why do we use a new algorithm? Can't we reuse the leader election algorithm we used earlier for consensus?
The leader election algorithm. But leader election is not the same as consensus.
Yeah, but if we can elect a leader, then the leader sets the value.
That's a very good question. So the question is, why don't we use leader election, and we elect the leader, and then the leader determines what is the consensus? That actually you can do that. And that is kind of the heart of a consensus algorithm called Raft. Actually, the most recent consensus algorithms are doing that. And so what they do is they elect the leader, and then the leader imposes the value. The problem is making it work when you have on a partially synchronous system. Okay, because you might have mistakes in the failure detection, so you have to be very careful. You have to do some kind of a majority election. Okay, and so it's a little bit tricky, but it can be made to work, and we will go back to that. Okay, so this is a very simple one. But the one that I just said, it's actually a little bit subtle to get it really working. but I will explain it later in the course. Okay? So this is an algorithm called raft, and its leader election is just one part of it. The problem is, what if the leader fails? Okay? And what if the other nodes are detecting that or mistakenly detect that? It has to still work. Okay? So there's some subtlety to make it really work in a partially synchronous system, especially since it's uniform consensus that we want to do. We want to be, so you can't just decide so quickly. But yeah, you can do that, and the most sophisticated, the most recent consensus algorithm is actually doing that. Okay? But it's not so simple as you seem to think it is. If you work out the details, there's some subtleties. But we get to that.
How is it different to this algorithm? Just that this algorithm.
This algorithm is based on the perfect failure detector. And that is what will let us go from one round to the next. So you really can execute in a very nice step-by-step way, which you cannot do if you don't have a perfect failure detector. You have no idea when the nodes are failing if you don't have a perfect failure detector. So you cannot go very nicely step by step. So this is a very simple step-by-step algorithm. Okay? You cannot do that if you don't have perfect failure detector. Okay? But we will slowly get to that. Okay? Here, the whole thing is based on the fact that all the nodes can, in a clean way, go from one round to the next. And you don't have to do any kind of election or synchrony for that. That is why this algorithm works. And that only works because you have a perfect failure detector. And so, but I will explain, bear with me. How do you go from one round to the next? There's a condition here. Here I increment the round number. So far, the nodes kind of magically go to the next round. Okay? They go to the next round. How do the nodes know? How does node 2 know all of a sudden I'm in round 2? How does it know? That actually is what makes this algorithm work. We can make it know. And it only can do that because of the perfect failure detector. That's the reason why. And I'll explain it here, but then I'll explain it also later on when we talk about the proof. Okay? How do I know? How does node 2 know that we're in round 2? Well, there's a trigger condition. Okay? Either it has actually got a message from node 1 and it has got the message, or it detects that node 1 has crashed. So the crash, this is that either it got a message from node 1 or node 1 has crashed. This, you can only know that if you have a perfect failure detector. Perfect failure detector is a very strong thing. So you can rigorously go to the next round. You are guaranteed that this node has crashed. But only because you have a perfect failure detector. Okay? So this algorithm really is built on top of this perfect failure detector. Okay? Okay, let's go into the the properties and show why they're correct. So first of all, validity. Validity means that you will only decide something that has been proposed by somebody. Well, if you look at this algorithm, whatever you decide will be your value, or a value that has been sent to you by somebody else. So it's someone else's proposed value. Okay? So you're guaranteed that it will only be a value that's proposed by somebody. Okay? What about integrity. Integrity means you only decide once. So you can prove that because a node will only decide when it's leader. But it's only leader when the round is making it leader. So every node will only be leader in one round, so it will only decide once. Okay? So that proves integrity. You only decide once. Also, it's all based on the perfect failure detector. And the termination, okay? How do we know this whole thing is going to run all the way n rounds? Okay? Okay? If a leader fails, we are relying on the completeness of P. That means the perfect failure detector will know that and we will go to the next round. Okay? And if the leader is correct, then we are relying on the best effort broadcast, that everyone gets it, and then either of these two will allow you to go to the next round. Okay? So because of these two, you know that you can step through all the rounds. Okay? Okay? And the final one, no two correct nodes decide differently. That one, it's true because there will be a correct leader with minimum ID number, okay? If I have n nodes and some of them crash, we take the first one that does not crash, okay? That one is correct. It will decide, and it will decide V, and it will best effort broadcast V, and every correct node will get the V. So from that point on, the nodes will only know V, okay? That means no other node will decide differently. So all the previous nodes from this one have crashed, and all the succeeding ones have adopted V. That means that nobody will decide differently, okay? So that proves that this algorithm is doing it correctly. Okay, how many failures can this algorithm tolerate? How many nodes can fail out of n, and this algorithm will still work? What do you think? We have n nodes. How many nodes can fail and it still works? One, two, n over 2. You need at least one node to decide, yeah? N minus 1. Yeah, that's right. Exactly. N minus 1. This algorithm will work up to n minus 1 failures. Only one node has to remain to make a decision. And it will work, because if it's node 33, as soon as you get to around 33, that node will decide. And that one is correct. If all the other ones crash, that one still decides. Okay? So n minus 1, okay, is what this algorithm tolerates. So this is a very simple and nice and strong consensus algorithm. It's not uniform, but let's make it uniform. We can actually make this algorithm uniform. In order to do that, let me introduce another pseudocode, okay, for algorithms. Another pseudocode that actually might be more readable. Instead of doing event and triggering when the event arrives, we actually have now each node running code here, but the instructions here can be kind of concurrent and synchronizing. Okay, so in this, I'm going to now show you the same algorithm in a different notation, that looks more like languages that you've seen before. Each node here, pi, runs this code, okay? And the only thing different is the number I here. For each node, the number I is like wired in. So for node 1, this will be if r equal 1. Okay, for node 2, it will be if r equal 2. Okay, so this is like a procedure that's parameterized by the node number. And the same code then is running on all the nodes. Okay, so how does it work? Well, it's basically a for loop. For r is 1 to n. R is the round number. If r equals I, that means the node is saying the round number is I'm the boss, okay? It starts by r equal 1, and p1 will say if 1 equal 1, and then I'm the boss. In round 2, p2 will notice that it's the boss. So this if statement, this code is only executed by the leader, okay? This if statement. Out of the n nodes, only one node will be executing this, okay? And what does it do? It does a best effort broadcast, which is this. For all j in 1 to n, send my proposed value to pj. So this statement is doing a best effort broadcast. This is pseudocoda, so I will invent any instruction that I need, okay? This is not an existing language, okay? If you want to make a language, you can do it. But this is to make it very short. And then I do decide xi, okay? So this decide will send the message back up. And now we go to the next round. Now we have an interesting instruction called collect. Collect this from R. Okay? So the collect statement is basically going to receive the thing that was sent. Okay? And it's also doing failure detection. So this collect statement is very interesting. It's synchronizing here. It either gets the message from node R. In that case, it updates its local proposal, or it notices that node R has failed, and it doesn't do this. Okay? It's false. Collect something from R is false if you detect PR has failed. Okay? So this collect message is kind of doing the synchronization from one round to the next. Okay? You see, it's true if it receives the message, and it's false if R has failed. Okay? So this collect message makes the nodes somehow talk to each other. Okay? So you see, this is very interesting notation for writing distributed algorithms. And it's like it's doing the same thing as the code before. So here I will show you again the code. This piece here, the deliver and the go to the next round. So the collect message, the collect thing is doing these two actually, yeah? It's going to the next round, it's doing the failure detection, but it's also receiving the message if the node is not filled. Okay? So this is interesting notation, right? This is a different kind of notation for writing the algorithm. This kind of shows in a more compact way how the nodes are talking to each other and how they synchronize and how you go from one round to the next. So this collect statement, when it returns with true or false, that's when the for loop goes to the next iteration. So that's how it knows that it has to go to the next round. Okay? So you see, it's kind of interesting. Most programming languages will not do this, but it's interesting to introduce the synchronization as part of the language operations. Okay? Okay, so now I've shown you a consensus algorithm that works fine, but it depends on P. And it's not doing uniform consensus. So the next two steps are, first I want to do uniform consensus, and then I also want to go to eventually P. Okay, so this is the easiest one. This is regular consensus based on P. So this is the most simple one that we just saw here. And now the next steps are going to be this and this. And the internet algorithms are actually doing both of them. So the Paxos algorithm, which I mentioned, the Raft algorithm, which is kind of a modern version, they are both internet algorithms doing uniform consensus. So we're only in the first step here. So the next step is making it uniform, but I won't tell you that today. You have to come back tomorrow. No, remember there is a course tomorrow, and tomorrow you will understand everything. Tomorrow I will go through everything, all that, and then you will be really masters of consensus. Okay. Today we've only seen the first one. So let me stop here for today. In this very quiet week, smart week, we're going to talk about consensus, and today I'm going to show you how to go to internet, eventually perfect failure detectors with consensus, and it's actually pretty hard for consensus to do it. First, a few seconds of silence for the Ukrainians who are fighting for their freedom and for our freedom. Okay, so we saw yesterday the hierarchical consensus. Let me recall it, but let me use this notation. The important thing about this notation, the special thing, is this collect operation. Let me write it here. Collect, and it gets a record. The collect instruction from a node. This one actually synchronizes. It waits, and there's two possibilities. It can either receive the message, this one, and then it returns true, or it detects the crash of the node R, and it returns false. You see, this one is basically the operation that lets us go from one round to the next. We know that we are going to have one of these two events. Okay? We will receive a message or detect a crash, or both. It's not important. We'll have at least one of these events. And if we receive the message, then this is true. So this can be used inside an if statement. So the way it works here is we have a for loop. This is running on every single node, and it iterates from 1 to n, and when the loop gets to the number of the node, then the node knows it's the boss, and it can do a send. Okay? It will send its decision to everyone. It will decide. Okay? And the collect is the one receiving it. Notice this if statement here will only be executed by one node. No? Okay, but everyone executes the collect. If the node is correct, if they collect, everybody collects, then they will get this value, and this one will decide. And then you go to the next round. Every node decides in the round in which it's the boss. Okay? And the orphan messages, remember these old messages coming from old rounds. Maybe if the old leader crashes, the message can still come in. This one is dropped. We saw that there's a simple condition on the number of the round we can use to drop them. So the collect drops it. So this very interesting instruction collect lets us write the code like this. It's not event-based, but it looks more like a standard language. Notice this is actually very interesting kind of a concurrent program, because the send is being sent from one node to everybody, and everybody will get it through the collector. Okay? This is our algorithm. Now, I want to move to uniform consensus, but also to eventually perfect detectors. We'll see uniform is not so hard, but going to eventually perfect detectors is actually quite hard to not get mixed up with the mistakes. Okay. But first, let's go to uniform consensus. Okay, that one is quite easy. We can, if we take this decision here, and we just move it to the end, then actually it will become uniform. Okay? We move it here. That means by the time we end up here, we have done all the rounds. All n rounds are done. Okay? And that means all the correct nodes have already gotten the value. Okay? And that means even if the nodes fail, all the correct nodes will have gotten the value, so we can put the decide here. So if it crashes, if a node decides and then crashes, what happens? Well, all the correct nodes have already gotten the message. Okay? So this is our uniform consensus algorithm. Okay? That's one thing. So it works. So the code I showed you, the hierarchical consensus, it is also, we can easily make it uniform. Okay? But it relies on a perfect failure detector. This one lets us move from one round to the next. Guaranteed that the crash detections are true, are correct. Okay? Okay, but let me show you now that the algorithm does not work with an inaccurate failure detector. So inaccurate means eventually, yeah? Eventually means that in the beginning, it's allowed to make mistakes. So it's inaccurate, and eventually it stops making mistakes. But in the beginning, it makes mistakes. Assume now, I'm going to show you the algorithm, the first version, the non-uniform version, where we have mistakes. P2 suspects P1, P2 thinks P1 crashed, and P3 suspects P2. Okay, that's possible. It's a mistake. Okay, so what happens? The execution. Well, P1 is correct, so it's going to decide and it will broadcast A to the two others. But P2 suspects P1, and so this A will not arrive there. It doesn't, we can make it so it doesn't arrive. Okay? That means P3 will get the A, but P2 will not. And now we move to round 2. Okay? For P2 it's easy. He thinks that P1 crashed, so we can move to P2, to round 2. And now P2 is going to decide. Okay? Sending the Bs. This B going up to P1 will not do anything more. This B going down will not arrive either because P3 suspects P2. Okay? So P3 still thinks it's A. And then eventually we get to round 3. P3 decides A. P2 decided B. P1 decided A. That's not good, and they're all correct. So you see, the algorithm doesn't work if the failure detector makes mistakes. The uniform one also has problems, also doesn't work. Here, let's assume P2 suspects P1, P3 suspects P2, and P1 suspects P3. So like in a chain, each one suspects the previous one. And the decisions are going to be done at the end. Huh? So P1 proposes. We know it's going to decide something. Huh? It proposes here, A. This A does not arrive. Then P2 here. In round 2, we'll send B, but this B does not arrive. And then we get to round 3. Okay, the B has arrived here, so this one will decide B. The A here arrives here, so we decide A. Here we decide A. So again, it's not good, huh? No agreement. So the hierarchical consensus does not work if the failure detectors are inaccurate. Okay? Okay, so let's try to figure out things. This one uses P. Can we make a consensus algorithm that uses a weaker detector than P? And I'll show you first the strong detector, and then we'll start talking about eventual. Remember we saw this funny detector called S. I'll remind you what it means. The strong detector, so it's strongly complete. It detects every failure, but it has only weak accuracy. That means it is only accurate with respect to one node. So it's weaker than P. P is accurate with respect to everybody. It never makes mistakes. Here it only makes no mistakes with respect to one node. There's only one node that really can be seen by everybody. That's what's called the strong detector S. It's called strong, but it's weaker than P. The name was given a long time ago, and the name has stuck. So the S detector only has a good view to one node. But that's okay for hierarchical consensus, because hierarchical consensus goes through all the rounds, from 1 through n. So that special node will somewhere be the leader. There will be a round in which that special node will be the leader, and that round, everybody will get the value. So we can prove it. We can prove that the hierarchical consensus works for strong detector S. It only has to be correct with respect to one node. We prove all the conditions here. So validity means it's doing the work, so it's only deciding on its own proposal or adopted value. That doesn't change. The values are sent coming from the proposals. Integrity, you only decide once. Well, the rounds are increasing monotonically from 1 to n, and you only decide when you're the boss, so clearly you're only deciding once. And termination means, will every node correctly advance round by round to make it to the last round? Okay? And it works because S is complete. S will detect failures. The fact that S makes mistakes is not important, but when there is a failure, it will detect it, and that will force the node to go to the next round. Okay? And if it's correct, if there's no failure, you will still get the best effort broadcast. So that means you will make it to the end. That's good. Then we have the final one, the uniform agreement. Okay? That the nodes will not decide differently. Okay? Okay? Now, there will be one leader that is accurate. That means the nodes will not make a mistake. They will not think that node has failed. Okay? And the node is correct and they will know it. Such a node exists because S assumes that. That node will do best effort broadcast. Everybody gets V. In the subsequent nodes, all will make decision V, okay? By all, and because the decision is done at the end, the uniform version, they will all decide V at the end, okay? You see that? It's because there's this one node and because you go through all the rounds. So that's nice, right? This one works also for this one. We only need to have one node, but it's still not an eventually perfect detector. So we have to go to the hard thing. What about eventual detectors and consensus? That's actually a very hard problem, and people work very hard on this. And to start this, I will make a theorem telling you that there's something that's not possible. There is a limit. Remember that hierarchical consensus worked for n-1 failures, but for eventually perfect, you cannot have any algorithm that will work for n/2 or more. So the number of failures you tolerate. So if there's n/2 failures or more, it cannot work. And we can prove that. And I will show you now the proof. A proof by contradiction. Okay? So assume we have an algorithm that uses eventually perfect detector and that tolerates n/2 failures. I'll show just an example. You have 10 nodes and 5 are failed. Okay? I will prove to you now that this algorithm cannot exist. Okay? By contradiction. So we assume it exists. Yeah, please close the door. Thank you. So we're assumed now that we have a uniform consensus algorithm that works in this case using an eventually perfect detector. Okay? And I will show you a contradiction. Assume we have 10 nodes here, 5 green ones and 5 blue ones. Now assume 2 executions. In the first execution, the green nodes are correct and the blue nodes have crashed. That's possible. And the detectors are behaving perfectly. They make no mistakes. That means all the detectors will detect these crashes, and the algorithm tolerates that, okay, according to our hypothesis. So the algorithm should work, and since all of these nodes are proposing 0, this one should give 0 as the consensus result, right? It's what it has to do. But now, maybe you can imagine what I'm going to do. I'm going to look at a symmetric situation. Here's another execution. Another very nice execution. In this execution, the green nodes all crash, and the blues are correct, and the detectors are perfect. That means the blue nodes will detect these failures, and each of the blue nodes has proposed 1. And since our algorithm tolerates 5 failures, it will give consensus 1. So that's fine. So this seems reasonable, right? But can you imagine now what we're going to do? We're going to take these 2 executions and we're going to combine them to make an execution that could happen where that there will be no agreement. Okay? Assume now I'm going to make a 3rd execution. I will actually combine the 2. And I can do it because the eventually perfect detector is allowed to make mistakes. So for a certain time, t0, this was the time that the green nodes needed to decide. The green nodes suspect the blue are dead. So for the first t0 seconds, these green nodes will suspect those. That's exactly the same as this. That's exactly the same. From the viewpoint of the green nodes, it's like the first execution, so they will decide 0. Okay? They see no difference. And on the other side, for a time t1 seconds, the blue nodes will suspect the green to be dead. And that's exactly the same as this execution. The blue nodes see no difference. Okay? Of course, it's a mistake, but they don't know that. So the blue nodes will decide 1. So now what happens? All the nodes are correct. Half of them have decided 0, and half of them have decided 1. That's not a good consensus. You see, we've taken these two executions, and we've shown that there is a possible execution where the algorithm will not work. You see how we've done that? We're actually doing execution engineering. Yeah? We're combining executions. You see how we did that? This is called partitioning argument, where we take executions and we make an execution that could happen and that is incorrect. So that's a contradiction, so the algorithm cannot exist. Okay? So it's not possible to have uniform consensus that works with eventually perfect and that can support n/2 failures. Not possible. Okay? So this can be made completely formal. We're not looking at time, we're looking at executions. Prefixes of executions. We have 2 schedules for the 2 executions. Here we have the events of the green nodes, and here we have the events of the blue nodes. If we take these 2 partial schedules and combine them, we have a new schedule that is perfectly valid because the failure detector is allowed to make mistakes. The green nodes are allowed to think that the blue have crashed. And the third one is incorrect. Okay? So, it doesn't work for n/2. So if it works at all, it has to be less than n/2, right? Is consensus even possible with an eventual one? Yes, it is possible, and this was a major discovery, or discovery, it's a property of the model. And we will show it for eventually S. So I will show you the algorithm for eventually S. That means the detector can make mistakes, but eventually there's one node that it does not make mistakes for. Okay? So eventually S is weaker than eventually P. So, will the algorithm also work for eventually P then? What do you think? It works for eventually S. Will it work for eventually P? I'm not hearing anything. What? Will it?
Yes,
Yes. Why?
because eventually S is reducible to eventually P.
Yeah, that's true. But can you maybe give the intuition of that? What's going on?
Eventually S is a simpler problem than eventually P, so solution for eventually S
Yeah.
can also be advanced.
Yeah, but there's more intuitive way of saying it. So eventually P makes, after a certain time, it makes no mistakes with respect to any node, but eventually S is still allowed to make mistakes for most nodes except for one. But we could have a especially nice version of eventually S that doesn't make mistakes for any nodes after a certain time. Of course, most eventually S's won't be like that. See, that's kind of the intuition. And eventually P, it has to do more work. We're demanding more of it. It has to make no mistakes with respect to anyone. Whereas the eventually S is still allowed to make lots of mistakes, except for one node. Okay, so this algorithm will work for eventually P. So that means it is possible. But actually, it's quite tricky. But I will show you the algorithm now. So we're going to go through the algorithm. Okay? And it's nice to explain it with eventually S, because it's also going to go through rounds, and at some point every node will be the leader, And so we only really need one node to be visible, to have no mistakes. We could do for eventually P, but it's nice because we only really need it. It's like kind of generalization of the hierarchical one. So eventually strong, I recall it, so it's strongly complete, so it detects all the failures eventually, and it has weak accuracy, but eventual weak accuracy. That means after a certain time, there's one node, at least one node, a correct node that is never suspected. Okay? That is the condition. Maybe there's more. Maybe it's as strong as eventually P, but it doesn't have to. Only one node is seen well. Okay? So it's like eventually P, but accuracy with respect to one node. Okay? And the algorithm I'm going to show works for this. So remember the eventually S, Okay, so we're going to generalize the hierarchical algorithm we did before. Of course, the hierarchical algorithm will not work. We saw it won't work, but it's actually you can actually say it in a more concise and precise way. Eventually, we don't know when it is. It might be after n rounds. The hierarchical one goes from 1 to n, and then it stops. And then it stops. But maybe the detectors are still making mistakes. Eventually, it might be later than that. Okay, so that's why it cannot work. So what do we do? Well, there's a simple idea. And actually we can make it work. The basic idea is to go around, do the rounds forever. So after round n, you start again at round 1. So 1, 2, 3 up to n, and then again 1, 2, 3 up to n, and you keep going as long as it takes. This is called the rotating coordinator, okay? So eventually S tells us that all these nodes will be correct with respect to one coordinator. Okay? And that's it. Once that happens, that coordinator will broadcast the value, and we're good, and everyone can decide. Right? Of course, there's a small, teeny, tiny, minuscule little problem there. Do you notice what the problem is? What is the problem here? I mean, eventually the nodes will be correct with respect to one coordinator. Everyone will adopt the coordinator value, and we're good, right? Yeah, but it's not quite so simple. Why not? Why not? Do you see why? We don't know when it's going to happen, okay? How do we know when? We keep going, and eventually, but sometime we have to stop. We can't just keep going to some random time. We have to actually know when to stop. That is the trick, okay? And that is actually a quite subtle trick. You see the point here, You see what's going on, How do we know when to decide? Rotating forever, that's good. It just keeps going as long as it takes. Eventually all nodes are correct. Fine. But how do we know that? You see, it's not so simple, You can feel the difficulty here, Right? That it's not so easy, Okay. Okay, but we can do it. We can do it, and it's actually quite clever. And the person who first figured that out is a quite clever person. Okay. Now we saw that the number of failures for eventually has to be less than half. But actually, this rotating coordinator, we can make it work if we have less than a third of failures. If we have less than a third failures, then we can detect the termination. So we assume that only that the number of failed nodes is less than a third. So if there's 10 nodes, 3 nodes can fail, but not 4. Okay? And we have to reason, of course, about this. The algorithm is actually a simple generalization of hierarchical consensus. It's not really much more complicated, really. It's just going forever. The trick is, how do we know for sure that we are allowed to stop? Okay? So that is where the subtlety comes in. So the algorithm is actually very simple. You're going through the rounds, 1 to n, 1 to n. And in some round, C is the coordinator. So every round is a coordinator. Everybody sends their vote to C. So all the n nodes send a message to C. C receives these messages, sees what is the majority vote in there, and broadcasts the majority to all of them. So if you want to make a picture, you kind of see it like this. So I'm going to make a picture, or maybe I erase something. Make a picture. It's good to have a picture to understand what's going on here. So we have n nodes. 1, 2 to n. And here's the coordinator. 1, 2, C, n. And we have the rounds. Okay. And the rounds keep going on. So let's say we're in round C. So what happens is everybody sends a message to C, to the coordinator. The coordinator picks the majority. Okay, and then sends that majority value back to all the others. And all of them will then adopt that maximum, that value. Okay, and then you go to the next one, huh? You keep going. So that's what happens in every round. And that just goes on forever until we have this magic detection and we know we can stop. Okay, but let me show you the code of the algorithm. I'm going to show it using the same notation that we did for hierarchical consensus. So the same code will be running on all the nodes, and you have the same, this collect thing, which lets you go from one round to the next. Okay? So here we have a while loop now, not a for. While true, R is the round number, R is just incremented, C is the number of the coordinator, R mod n plus 1, from 1 to n, from 1 to n, and so on. All of them send value to the coordinator. And now in the middle, we have the code that's executed by the coordinator. Okay, so this code is run on all the nodes. But only if I is equal to C will it actually run. So the node number, C is the coordinator, the node number I, only the one that's equal to C will run this if statement. Okay? Now, all the nodes have sent a message to the coordinator. Here we have a for loop. We're only waiting for n minus f messages. Okay? Why n minus f? Well, we have less than f failures. Okay? So we know that we're going to get at least n minus f messages. We know for sure. So if we wait for more messages than that, it might block. Because we might have failures. But we know we're going to get at least n minus f. Fine. So we wait for n minus f, and we receive the thing that was sent. And for simplicity, all the nodes will either propose 0 or 1. Okay? They will either propose 0 or 1. So the xi, the proposal, to make it simple, it's 0 or 1. You can generalize it, but I don't want to do that because it makes the code more complicated. Doesn't add anything. So we will count the zeros and we will count the ones. Okay? And so we have an array with 0 and 1 index. We receive the value from some node and we increment the right element of the array, yeah? Either messages 0 or messages 1. So you understand this, huh? C-like notation. Okay? So we do that. We've received n minus f messages. Now, what is the majority? If we have more zeros than ones, then v will be 0, else v is 1. Okay? And we will send v to all the nodes. So basically we pick the majority, the value that is the most often here, and we send that one to all of them. So if nobody fails, then we know for sure that all of the nodes afterwards, all of them will of course get the majority value, okay? Fine, but still we have to guarantee that it'll stop, huh? Okay, yeah?
There is no protection to verify if a node sends a multitude of messages.
No, we're assuming that the nodes will send only one message here.
So if we have a Byzantine node in the
This is not a Byzantine algorithm, huh?
yes, but if we have an evil node in the system, they can just choose the value of the.
Sorry, if we have what kind of a node?
An evil node.
An evil node. Yeah, we're assuming no evil nodes here.
Okay.
If you want evil nodes, then we go to another level of complexity. We won't go into that here. Then you have to do all kinds of things with digital signatures, but we won't do that here. So the nodes here are not evil. They're honestly doing consensus. They send, and you have to do the consensus among the n nodes. Okay? No evil nodes. Okay? Each node, now we're back again to code that's executed everywhere. Huh? Each node will receive the outcome from the coordinator, or not, because the coordinator might crash. Huh? Or there may be a false detection of crash. Mistake. But it may actually receive, and if it does, it sends its local value to v. So notice, even though the coordinator sends messages to all the nodes, in the beginning of the algorithm, maybe none of them arrive. Because all of the nodes think the coordinator has failed. They're allowed to think that. In the beginning, they're allowed to make mistakes. So we're not even sure, in the beginning, that any of these nodes will receive it. And in the worst case, none will receive it. All we know is that eventually, there exists one node from which we will receive it correctly. But we don't know when. Okay? But eventually. It's kind of tricky. Okay, so now what I want to do is I want to reason about this algorithm. And the very important things to remember are f is less than n over 3. Also, the fact that we're getting n minus, that we're waiting for n minus f. So the coordinator waits for n minus f messages. That's also important. Okay? So this is going to be very important now. And now we want to reason about this. So this is the algorithm. Okay? So you understand what it's doing, yeah? There's no ambiguity, yeah?
How can the algorithm know the f in advance?
That's an initial hypothesis. When the whole thing is set up, we are saying we guarantee that the number of failed nodes will be less than n over 3. But we don't know the value of f. It could be any value less than n over 3. All we know is that it will never be n over 3 or greater. So if we have 10 nodes, f could be either 0, 1, 2, or 3. But we don't know which. Okay?
If we loop through the node and we index the nodes by the number, we might miss the ones that fail. If we say that f is 1/3, but we look for
Well, if we loop, if node C has failed, then during this round, this piece of code will not be executed, right? And all the collects will detect failure, because the detector is complete. Huh? If the node has failed, it will say it. Huh? So if we go through a failed collector, is that a coordinator? Is that what you're saying?
Yes.
Well, then this piece of code will not be executed at all during that round, right? But these two pieces will be executed because they're executed on all the other correct nodes. So we're doing a send to a failed node here, disappears. And now we're trying to collect a message coming from a failed node. Well, the collect will return false because it will detect the failure, right?
But in the for loop, we look
The for loop, well, in all the nodes that are not the coordinator, I will be different from C, so it will not execute this code.
Yeah, but if we are the coordinator and you have to do...
If you are the coordinator, but you failed, or what?
No, if you are the coordinator...
The coordinator changes, huh?
Yeah.
Every node will be coordinator, huh?
Yeah, I get that, but the for loop inside the code for the coordinator has
This
to-
one?
Yes, it iterates through every other node, right?
No, it's receiving, huh? It's only collecting receiving messages, huh? Or you're thinking of this one, the send one?
No, the out one.
This one? I'm collecting messages. So assume the coordinator is running. Here, it's running correctly. It will receive messages. It will wait for messages to come in. Right? But we won't wait for end messages.
So we don't
Yeah.
specify who to receive the message from.
No, we don't know. I mean, we will know when we receive, but it doesn't really matter
Okay.
from who we get it from. It's only the number of messages that's important. Okay? Okay?
Yeah,
It's
okay.
good. It's important because we're reasoning on this now. Huh? So you have to understand very well this code. Clearly, there has to be no ambiguity, huh? Because we're going to do some reasoning on this code now. Using this condition. F is less than n/3. Okay? And there's going to be some interesting, so you might say, why n/3? Why not n/4 or n/2? Well, when we do reasoning, you'll see why. You will see why. Okay, so let's go on now. So this is clear, right? Everybody understands that code. I should have a second screen so it stays busy. Okay. I'm going to do the reasoning in 2 steps. Okay? And the first step is this lemma, and the second step will tell me the termination. Okay? So 2 steps. This lemma, I call majority lemma. If at least n minus f nodes vote V, then every leader will see a majority for V in all rounds greater than R. So as we assume we have a round R, or C, we're here, and n minus f nodes vote V. So they will send V. They will send V to the coordinator, at least n minus f. Okay? Then what we're saying is the majority will always be V later on. Okay, let me show you the reasoning for that. Okay, step by step. All the nodes vote. The coordinator waits for n minus f messages. You get that, huh? Okay. Now, how many of those messages will be equal to V? Well, not the n minus f. N nodes are sending messages here. Huh? N nodes are sending messages, and some of those nodes might fail. Okay? And the ones that fail, it might be ones that have chosen V, okay, that fail. Okay? So N minus F will vote V. Okay, we know that, huh? But of these N minus F, F can fail. So we know the coordinator will get at least N minus F values equal to V. You see that? So N nodes are sending messages. The coordinator waits for N minus F, huh? And N minus F are voting V. But how many V's will the coordinator get? Well, maybe not N minus F, because some of these guys might fail. You see that, huh? F can fail. So we know the coordinator will get N minus F values equal to V, at least. You see that? Okay? And because it's waiting for N minus F, there's F other values, because the total number of values it's waiting for is N minus F. It will get at most F values different from V. Okay? Now let's compare these two. Which of these two numbers is bigger? The N minus F values that are equal to V, or the at most F values that are different from V? We can compare those two. So which of these two numbers is bigger? Well, it's actually this one, and it's a consequence of F less than N minus 3. Okay? So we can do the calculation. It's not so hard. F is less than N over 3. That means 3F is less than N. Right? Well, I subtract 2 F's. F is less than N minus F minus F. Magic, the magic is done. You see the magic here? This is why we need N minus 3. Because of this, we know that the coordinator will guaranteed get more V's than anything else, even though we have failure. Isn't that a neat trick, you guys? What do you think of that trick? You should meditate. It's actually a very important, neat trick. Because with this we can vanquish, we can conquer the eventually P problem. Okay? So, we know that F will be less than N minus F minus F. So the majority that the coordinator gets is guaranteed V. And the majority will always be V. It will never get less, because the coordinator will just send V's to everybody else. So there can only be more V's afterwards. Huh? So in the future, it will always be V. It will never decrease. Because someone who was not V might receive a V. So in the future, if we have this situation later on, it can only give you more V's, okay? Or the same number. This is the key reasoning. This slide gives you the key why it works. And notice the F has multiple rows here, huh? You have F failures. So you wait for N minus F messages. But those N minus F can also fail. So it's N minus F minus F. And that has to be greater than F. So you have 3 F's in there, huh? Okay? So that's why F has to be less than N over 3. That's a neat trick, huh? You have to admit it's a neat trick, huh? And it is completely the reason why we can do consensus. Okay? So this is only the key, this is the key thing. So we know that every leader will see a majority, but now we still have to terminate. But actually that's not so hard. Now we have this, we can actually figure out when to terminate. Okay? Okay. So the coordinator is always waiting for N minus F. Some vote 0, some vote 1. The coordinator picks the majority. So actually we can show that if all of the N minus F are the same, they're either all zeros or all ones, then we can terminate. Okay? If we get n minus f that are all the same, we can terminate. Then we can stop. So that's something we can prove also. So the code would then looks like this for the full algorithm. So in the gray here we have the algorithm. We have to add a little piece of code for the decision when to stop. Okay? So all of the values here, so we get n minus f, we know we're getting n minus f, maximum f failure. If there's either no zeros or no ones, then d is equal to 1. D means we decide. We can decide, we can finish. And it's the coordinator that decides. And the coordinator sends the outcome with the d to everybody. Okay? And all the other nodes will collect the d. Okay? And if the d is 1, okay? And also, we have to make sure we're not deciding more than once, then we decide. And that's it. Okay? So the coordinator can decide if all of the n minus f are the same. Okay? Because then we know we're done. And I will prove it now. The termination. Okay? And this is now coming from the eventually s. Assume that there is some node that is the good one for the event, for the s. It will never be falsely detected. And it's late enough that we're past all the mistakes. Q will never be falsely detected. So eventually this Q will be the coordinator. The Q will get the majority. Everyone will collect Q's votes. But since Q is correct, and nobody is mistaking Q for anybody else, everyone will adopt V. Nobody will mistakenly think that Q is failed. So everyone who's alive will adopt V. From now on, all alive nodes will vote V. So the next time around, so you go Q plus 1, and the next time around, again when Q is coordinator, it will only receive V's because of this. And then it decides. Of course, this is a worst case, Maybe some other node in the middle also is okay, doesn't have mistakes. But we don't know that for sure. This is the worst case. There might be other nodes with no mistakes, but we're not sure of that. All we know is that there is only one that we're sure of, that's Q. So the first time we hit it, after the eventually part, it will pick the majority, and from that point on there will only be V's in the majority, as the lemma says. And then the next time it's coordinator, there will only be V's and nothing else, for sure, guaranteed. And then we stop. And then we can terminate. What do you think of that? That's a pretty clever algorithm, no? It actually works, All of that to get around this nasty eventually business. Because the whole point of eventually is you don't know when. But because we're bounding the number of failures, we can actually figure out when. Okay? What do you think of that? What do you think of that, you guys? Boom. Okay. Let's make a break now. We make a break. So you can see that it's subtle to do consensus and eventually correct for a failure detector. We're actually fighting several enemies, The fact that you can have many mistakes. Also, the fact that you can have failures, you don't know how many. And for the S, the fact that you can keep making mistakes with respect to anybody except for one. For that kind of an algorithm, there's no way you can hack it. You have to prove it. Okay? You can imagine, if we don't have a proof, how do you know this is correct? That there might not be some very subtle execution someday that will cause it to crash. It's not possible to know that without a proof. And that's why we prove all of the properties, okay? You prove them. Okay, let me summarize now consensus for now. So we solved consensus, regular consensus, using synchronous, partial synchrony, if you have less than n/3 failure. Uniform consensus, so we showed the algorithms, so the same algorithms as before will work for uniform consensus. So the eventually S with less than n/3 failure. So you can see the subtle reasoning we have to do to know when we can stop. And that's the reason why we have to limit the failures. This is actually not the best you can do. The best, you can actually reach the n/2 limit, the theoretical limit that we saw. You can reach it. Eventually P with less than n/2 failure. This is a famous algorithm called Paxos, invented by Leslie Lamport in 1989. And this is what really made distributed systems, internet systems, possible. But this algorithm is very complicated, so I'm not going to present this one in the course. But I will present a modern version of this one called Raft. This one was done in 2014, which is 25 years later than Paxos. Most modern systems use Raft. Raft is just as powerful as Paxos, but much easier to understand. And it uses leader election. Okay? I will not see Paxos in this course because it's very complicated, and I don't think that complexity gives you anything. It's like when I calculate the area under a curve, I'm not going to use a geometrical construction like Archimedes did 2,000 years ago. I will use calculus, okay? But the geometrical construction is very, very complicated. Archimedes was a very smart mathematician, but he did not know calculus. For similar reason, I am not going to show Paxos. You can see Paxos. There's even an article by Leslie Lamport called Paxos Made Simple. Okay? Yeah, sure. Okay. But the algorithm I showed you today explains the kind of reasoning you need to do to know termination. Why limiting the number of failures can give you enough information that you can stop. Okay? And of course, this works on partially synchronous. For an asynchronous model, consensus is impossible. Okay? Remember the two generals problem from the very first lecture? If it's truly asynchronous, it's not possible. This is a famous result, also a famous theorem called FLP. But this theorem I will not present to you either, because there's so many things to present in a course like this. You can look this up. But this is an impossibility result. That means there's always going to be an execution that will not terminate. It may terminate very often, but you cannot guarantee. In an asynchronous system, there will always be some execution that will go on forever. Okay? So that makes it not possible. Okay, so what I'm going to do now is I'm going to show you an application of consensus. Consensus is incredibly useful in today's distributed systems. I will show you an application called terminating reliable broadcast, and then, probably I won't have time today, but later in the course I will show you the Raft algorithm, okay? This is the one that you have to understand for consensus. But now let's show an application, a really interesting application, because it teaches you something special about distributed systems, okay? About what do you know in a distributed system. So let's say you have a chat, Okay? People are chatting over internet, and I reply, I send a message, ta-da. I don't know when, or even if that message will be delivered, okay? Or even if I know it is delivered, I don't know when. So I don't know when the other people will get the message. That's true for reliable broadcast. There's no time bound. You don't know when. Of course, if you can see the time-space diagram, then you could see when the algorithm is done, but the nodes don't see that. The individual nodes don't. But sometimes you want to see it. So a server is using reliable broadcast, and the clients are waiting. How long do they need to wait? Okay, to make sure they get it or will not get it. Remember, in reliable broadcast, there's two possibilities. Either all correct nodes get it, or no correct nodes get it. And if I'm waiting, and nothing is coming, which case is it? Well, I don't know. In reliable broadcast. Terminating reliable broadcast will solve this problem. It will always give you an answer, okay? You can always get an answer. Terminating reliable broadcast, it's the same as reliable broadcast, but it does a little bit more. So the sender broadcasts, the receivers wait for messages to come, and always a message will come. The message will either be M, or it'll be like a special message that tells me that it didn't work, okay? Sender faulty. Now remember, when the sender fails, then it's possible that nobody gets it. But in the regular reliable broadcast, you don't know that. But I want to know when it's done, when I can stop waiting. Okay? So TRB lets me do that. Always you will get an answer. It's either M or it says funny message, sender faulty. It's always one or the other. Okay? And sometimes that's useful. But in order to get that, we have to do work. Okay? And that work is not so simple. And here is the terminating reliable broadcast algorithm. It uses best effort broadcast and a perfect failure detector. And it has two request and indication, TRB broadcast and TRB deliver. It's slightly different interface. All nodes have to broadcast, even if they're not sending anything. If they send nothing, they can just put nil here. Okay? And then there's a delivery, but the delivery will either be M, the message, or it'll be a token SF, sender faulty token. Okay? And then you have the properties of this. Slightly different from the regular reliable broadcast. Every correct node eventually delivers one message. It's not true for the regular reliable broadcast. It might be 0. Validity, if the correct source sends M, then source will deliver M. That's similar. Uniform agreement, if any node delivers M, then every correct node will deliver M. So in that sense, it's kind of like uniform reliable broadcast. Okay? And integrity, this is like a node creation. If a node delivers M, then either the M is sender faulty, or it's an M that was actually broadcast. It will not create random messages. Okay? It's either M or SF. So this is similar to reliable broadcast, but different. The main difference is this one. Every node will eventually deliver one message. That means when you do a broadcast, every client knows that something is coming. And it's not true for regular reliable broadcast. Okay? Okay. So, How does it work? Okay. The source will do a reliable broadcast of M. Okay. But if the source crashes, if some perfect failure detector, P, suspects, if P suspects the source, then I will deliver SF. So the source sends the message M, but maybe it crashes. And if the receiver suspects, then it can do SF. But the problem is, similar to what we saw before, assume the source crashes. Well, maybe I get M, and then I detect the crash. Maybe I detect the crash and get M. So all the nodes are going to get different stuff. Some of them will get M, and some of them will detect the crash. So there's no agreement. They all kind of get different stuff. And we have to get around that. We have to make them agree. Okay? And the way to make them agree is to do a consensus. So this is an application of consensus. The consensus forces all the nodes to have a coherent view. This is how it works. The source will do best effort broadcast, and all the nodes propose. If they have a crash suspicion, they propose SF. Otherwise, they propose M. Okay, whichever comes first. They propose one of these two. And then you have consensus. Some nodes have proposed crash suspicion. Some nodes have proposed M. The consensus runs, and it decides. And all the nodes will deliver the decision of the consensus. And then we are sure that there will be all M's or all sender faulties. And if the sender does not crash at all, then all the nodes will propose M, of course, and then we'll have M. We have to actually, nobody will propose crash SF unless the source is actually crashed. Okay? So that's how it works. And we can prove that it's correct. So again, we're going to go through all of the conditions. Okay? So intuitively, it's very nice, right? If the sender is correct, everybody gets M. And if the sender is correct, nobody is suspecting the sender. So the consensus, of course, will decide M, because everybody has proposed M. That's good. It's only when the sender actually crashes, there's a chance that you can get sender faulty. Okay? And we can go through the 4 conditions. Termination means every node gets one message. Okay? And there's 2 pieces. First of all, the P, if the sender crashes, the P will detect it. And the best effort broadcast will also deliver if the sender doesn't crash. That means I'm guaranteed to propose one message, one value. And the consensus is guaranteed to terminate. So here I'm guaranteed that there will be one delivered. Okay? Okay? Now assume validity. Assume the source does not crash, sends M. Because it doesn't crash, all nodes will get M before suspecting, or they will not suspect. So they all propose the same thing, and so they will all decide M. So if the source does not crash, it's all fine. Okay? The uniform agreement, they will all decide on the same thing. Well, that's pretty clear because of consensus. And P is accurate, so it's not, if it says crash, it really will have crashed. Okay? Okay? And finally, that it will not invent message. Okay? So the best effort broadcast does not create anything, we know that. And consensus is valid, so all the decisions are values that we proposed. Okay? That means we will have M or sender faulty. Okay? So we're good. So that's terminating reliable broadcast. I'm not going to show the actual code. It's a nice exercise to write down the code and to do the events. So that's exercise for you guys. It's a question I might ask. Hint. Now I want to ask some questions, some subtle questions about this algorithm. Can we implement TRB in an asynchronous system? In an asynchronous network? Well, we use consensus to implement TRB, but maybe we don't need consensus. Okay? You can't do consensus, but in fact, if you have consensus is reducible to TRB, that means if you have TRB, you can implement consensus. And we know that consensus cannot be done in asynchronous networks, so TRB cannot either. Okay? So how do we do that? How would you implement consensus if you have TRB? So I have a black box that does TRB. I do a sender faulty or M. How do I implement consensus if I have TRB? It's slightly tricky, but not that tricky. How do I implement consensus? Given TRB, how do I implement consensus? I'm going the other way from the code. Now, the nice thing about TRB is that every node will receive a message. That means if I do n TRBs, I will receive n messages. Okay? If every node TRBs a proposal, I know I will receive n messages. So I can make a vector of n. That's only possible in TRB, not in regular RB. I have a vector of n replies, and this vector, it's actually the same vector for all nodes because of the agreement of the TRB, which was done by consensus, of course. So this vector is the same. So we have this vector, and now all we have to do is somehow pick something from this vector. Make a decision, okay? We pick an m, we make the first non-SF message, or what is median? Are there SFs in there, or messages in there? So if we have a deterministic function of that vector, then all the nodes will pick the same thing, and we have consensus. Okay? So that works because TRB, everyone always receives the message, and all the nodes will receive the same message, okay, from the TRB. So it's using consensus inside TRB. And we can use that to force the thing to work like a consensus algorithm. Okay? So here you see we're kind of doing in the opposite direction. We use consensus to implement TRB, but if we have a TRB, we can actually do a consensus by doing this trick. And you see, you have to think carefully why it works. It works for two reasons. One, every node will guaranteed get a value, not true for RB. Two, you have agreement. Each TRB will send the same value to all nodes. Okay, that's very strong. It's actually implemented by consensus. So it's not a surprise, kind of, that we can use TRB to extract, again, the consensus. Okay? So TRB is like just as strong as consensus. Okay? Another subtle question. If we have an eventually synchronous system with eventually P, can we implement TRB? Now, we use P inside of TRB, but that's not a proof. Can we implement TRB if we have eventually P? Well, we cannot. We cannot because, again, if we have TRB, we can use it to make a P. P is reducible to TRB. That means if we're given a TRB, we can force a P out of that. We can make it into a perfect failure detector. And that means TRB is actually equivalent to P. And we know that eventually P is strictly weaker in an eventually synchronous system. We know it's strictly weaker, so it's not possible. So how do we get a P out of TRB? So there's a trick. How, if I have TRB as a black box, how do I get a P out of there? Perfect failure detector. Well, it's kind of a trick. P is doing heartbeats, so we're actually going to implement P. Each node will regularly do TRBs. So it's like heartbeat. Every time interval it does another TRB. And the real point is that at TRB, every node will receive one message. And if I receive SF, I suspect the sender, and that's it. Okay? That would mean that I know that the sender has failed. If the sender does not fail, I have to receive M from the TRB, yeah? So the TRB, you can use it to implement a perfect failure detector. You see, it's kind of funny and subtle, huh? We're looking at different properties of the systems, huh? So the TRB, if the source is correct, all correct nodes will deliver M. Okay, that's good if the source is correct. But that means if any correct node does not deliver M, then we know the source has crashed for sure. That's the contra positive. If we get SF, we know the source is dead. Okay. So TRB is really synchronous, okay? It requires synchrony. Okay, so that's an application of consensus. We still have a little bit of time, but I'm not going to present much more. Let me just present at the beginning of a presentation on Raft. Just to give you an idea. So this is actually a conference presentation. This presentation was not made by me. This was made by the inventors of Raft, Diego Ongaro and John Osterhout. Okay. Raft. Conference advertisements. Okay. So they are presenting their intuition on distributed systems, availability or consistency. That means either you see the result, if you see the result, or, but it might not be consistent. Okay? Okay, so you want the system to be consistent, that it's all the nodes are doing the right thing. And this is okay, so I'm not sure I would present it like this, but look, in a big distributed system, if any point fails, the thing might go haywire, okay? Big cloud tools. So how do they make big cloud tools? Well, there's two ways. One way is a hack, which they call ad hoc algorithm. And many cloud tools were like this. Facebook was a pure hack in the olden days. It maybe is not a hack today, I'm not sure that it's still not a hack. So how do they program it? They just sort of write a piece of code, and sometimes the code will crash, but it's rare. So we're fine. Okay? So on Facebook, sometimes you send a message and it disappears. Weird things happen, or some weird thing appears on your wall or something. Yeah, who cares? It just happens. So that's a hack. So these guys, Diego Agaro and John Astor, are saying, no, you don't want hack, you want something good. So you want consensus algorithm. And Paxos, or Raft, or something else, like a library, or a service, a consensus service. So there are services that you can use. There's a service called Zookeeper, and the other services that have consensus built in. Okay? Good? So what is consensus? So this is not a course, this is a simple conference presentation. So this is not a real formal definition. So what is consensus? It's agreement on shared state, whatever that means, and it recovers from server failures autonomously, whatever that means. The minority of servers fail is no problem. This is what I said before, less than n/2. It only has a problem if the majority fail. Okay? Here I have 5 servers. If 2 of them fail, I'm okay. Okay? And let me give you a couple more slides, and then we'll be done today. So why do you need consensus? Well, what do you think? Well, if you want a big system to be consistent, transactions, which server is doing SQL is like database query. I have a storage system distributed. I have database state that's replicated. This is not a very clear slide. Why do you need consensus? But this slide is very nice. This slide shows you how a big distributed application is done. How do you make a big distributed application that's replicated on many machines and that's reliable? So I have a bunch of powerful machines. Each one of them is running the same code. These are the clients. These are the machines. So I have 3 machines running the same code here. Okay. So how do I do that? There's 3 parts. The code that's running is the state machine. So when you see state machine here, you have to see it can be any application, okay, that has local variables. It's a state machine. The log is the storage on disk. If it crashes and reboots, the log is safe. So this is the permanent storage. And then the consensus is what makes these 3 nodes agree with each other. So all large distributed applications with many, many servers handling many clients are all written like this. Okay, so this is a very nice slide actually. The application is running on every node. There's a log on every node, and there's a consensus module making sure that all the applications are in the same state. Okay, this is called a replicated state machine. All the servers execute the same commands in the same order, and the consensus module ensures that the log replication is good, is consistent. Okay? And like we saw, the server system makes progress as long as any majority of the servers are up. As we saw, you need a majority to be up. Okay? And the failure model, as we saw, is fail stop, not Byzantine. Okay? Messages can be delayed or lost, but you don't have Byzantine failure with evil nodes. The server is running in a secure environment. Okay? So this is the kind of application we're looking at. This is typically all big cloud applications are kind of looking like that today. Whether that's good or bad, I don't know, but they work like that. Maybe in 20 years it would be different, but today they're looking like this. Okay? And how do we do the consensus? Well, up to 2014, it was Paxos, invented by Leslie Lamport in 1989. The problem with Paxos is very complicated. The dirty little secret of the NSDI community. So these are network tool people, the professionals. At most 5 people really truly understand every part of Paxos. Or you have a a system called Chubby, which is a lock manager, which is supposed to do consensus. And they published a paper, and they say this: there are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. The final system will be based on an unproven protocol. What does that mean? It means they didn't really implement Paxos. They kind of implemented part of Paxos, and it's still buggy. That's what it means. This was in a published paper by Google, people from Google. So Paxos is too complicated, and that's why the authors, they want to design a system that is much easier to understand than Paxos. And this is 25 years after. After 25 years, maybe it's time to rethink a little bit. Okay? And so Raft is a better and more understandable system. Okay. But I don't have time to present Raft today. I think that 15 minutes is not enough. So let me stop here, a little early. I think you have seen plenty today. But it's very important to understand why this thing terminates. This is the key. This reasoning is actually one of the things that makes the internet work. Okay? That you can actually do termination detection in an eventually perfect system when you have failures. That is really non-trivial result. I showed it to you here for n over 3. You can push it to n over 2 for Paxos. So I'm not going to show Paxos, but I will show Raft where it's also n over 2. So you saw here how it works. So if the number of failures is small enough, then if you can reason about the operation of the system and figure out when you can terminate. That is very non-obvious result. Okay? Okay, so let me stop here. Thank you very much.